Atomic structure and source of charge. To understand where the phenomenon of electric charge comes from, the basic structure of matter needs to be discussed. All matter is made up of atoms, which are made up of protons, neutrons, and electrons. Each atom contains a central nucleus that is composed of protons and neutrons, otherwise known as nucleons. Electrons move around the nucleus in the empty space of the atom. Protons can be represented as P+, and they're positively charged. Neutrons can be represented as n to the 0 power, and they are not charged. Neutrons and protons together are called nucleons. They're located in the nucleus of the atom, and they typically don't leave. They're bound to each other by the strong force, which we will learn more about later. Protons and neutrons are not fundamental particles. They're made up of quarks, which are fundamental particles. The electron was discovered by J.J. Thomson in 1897, and in a series of experiments between 1909 and 1913, Robert Millikan and his graduate student, Harvey Fletcher, established the value of the charge, E, on an electron. Millikan and Fletcher's work in subsequent experiments have established the value of E as 1.602 times 10 to the negative 19th coulombs. The SI unit of charge, the coulomb, is a very large number of electrons or protons. 1 coulomb is about this many extra electrons. That would be a -1 charge. A +1 coulomb of charge would be this many lost electrons. Because small amounts of charge can generate large amounts of force, charge is often measured in millicoulombs, microcoulombs, or nanocoulombs. It has also been demonstrated that E is the smallest value of charge, with the exception of quarks, which will be covered later, and all larger charges are an integral multiple of this number. Thus, you can have a charge of 3.2 times 10 to the negative 19th coulombs on an object, but you can't have a charge of 3.0 times 10 to the negative 19th coulombs. The charge on any object is always an integral multiple of 1.6 times 10 to the negative 19th. Electrons are fundamental particles. They have no underlying structure. Electrons are represented by this symbol, E with a negative sign. Further research showed that the electron has a mass of 9.1 times 10 to the negative 31 kilograms. The charge on an electron is lowercase e. It is 1.6 times 10 to the negative 19th coulombs. And m sub e, the mass of an electron, is 9.1 times 10 to the negative 31 kilograms. This is how those constants look on the AP2 equation sheet. The mass of a proton or neutron is about 1,800 times the mass of an electron. In their regular state, atoms are electrically neutral, not because they contain no charge, but because they have equal numbers of protons and electrons. Their total charge adds up to 0. If an atom gains electrons, it has a net negative charge and is called a negative ion. If it loses electrons, then it has a positive charge and is called a positive ion. Like energy and momentum, charge is neither created nor destroyed. It is conserved. Opposite charges attract and like charges repel. As a result, negatively charged electrons are attracted to the positive nucleus. Despite the great mass difference, the charge on an electron is exactly equal in magnitude to the charge on a proton. An electron has a charge of negative E, and a proton has a charge of positive E. Despite what you might have previously seen, this is not what an atom actually looks like. If an atom was magnified so that the nucleus was the size of a baseball, the atom would have a diameter of approximately 5 miles. And the electrons would be approximately the size of the period at the end of this sentence. Atoms are almost all empty space. Since everything, including us, is made of atoms, that means everything, including us, is mostly empty space. Below is a picture of the Bohr model, created by Niels Bohr and Ernest Rutherford in 1913. It got some things right and wrong. Things it got right: the charge of protons, electrons, and neutrons, and the relative location of protons, electrons, and neutrons. Things it got wrong: protons, electrons, and neutrons do not have actual spherical boundaries, and electrons do not actually travel on tracks. Here's a more realistic visualization of a helium atom. The nucleus is buried deep within the atom and is 1,000,000 times smaller than the atom. The 2 protons and 2 neutrons are shown in red and purple. The width of the nucleus is 1 times 10 to the negative 7 nanometers. The diagram shows a magnified view of the nucleus. It fits within the darker circle. What is the significance of the dark circle surrounded by the lighter shades of gray and pink? You know that helium has 2 electrons, yet they're not shown in this picture. That's because we don't know exactly where those electrons are. We only know a probability of where they are. The darker the shade means that it is more probable that the electrons are at that location. It has been shown that electric charges move between objects. Based on this picture of the atom, which of the constituents of the atom look like they could move? Would it be the neutrons and protons buried deep within the atom, or the electrons? The electrons are the particles that will move between atoms. They're not bound together as tightly as the protons and the neutrons. Electrons are fundamental particles, meaning they're not comprised of smaller particles. As of now, physicists have not found any further structure within the electron.